Right now, the James Webb Space Telescope, in conjunction with SWIFT and SPHEREx, is observing the second confirmed interstellar comet, 3I Atlas, and the spectroscopic data streaming back from its coma reveals chemical ratios that contradict every model astronomers built for how comets from outside our solar system should behave, leaving the scientific community profoundly unsettled. The carbon dioxide to water ratio stands at 7.6. The carbon monoxide to water ratio measures 1.65. Those numbers might not sound dramatic at first glance, but to planetary scientists who have spent decades cataloging the composition of comets, they represent something close to an impossibility. Comets from the Oort cloud, comets from the Kuiper belt, even the strange objects that occasionally wander in from the outer reaches of our own solar system. None of them produce coma chemistry like this. The gas erupting from 3I Atlas as it approaches the Sun carries 7.5 times more carbon dioxide than water vapor. For comparison, Halley's Comet, perhaps the most famous periodic visitor Earth receives, shows a CO2-H2O ratio closer to 0.06. The interstellar object is outgassing more than 100 times the proportion of carbon dioxide that Halley does. Stop and consider that. The Discovery team, led by Romain Maggiolo from the Royal Belgian Institute for Space Aeronomy in Brussels, published preliminary findings 3 weeks ago, and the paper has sent ripples through the astrochemistry community. Maggiolo himself, in a cautious statement released through the Institute's press office, noted that the compositional profile we are seeing does not match our baseline expectations for interstellar material. That phrasing, dry and measured as it is, masks a deeper concern. When pressed during a virtual symposium last week, Maggiolo elaborated. We anticipated that an object traveling for millions or billions of years through interstellar space would show evidence of surface processing by galactic cosmic rays. What we did not anticipate was the degree of chemical complexity, nor the stability of the organic-rich layer we are now detecting. Here's where it gets interesting. The spectral signature of 3I Atlas does not merely indicate the presence of organics. The color readings and absorption bands match those of the solar system's most mysterious residents, the Centaurs and trans-Neptunian objects. These are bodies that orbit in the frigid outer regions beyond Neptune, exposed to the slow bombardment of cosmic radiation for eons. Over time, that radiation transforms their surface ices, breaking molecular bonds, rearranging atoms, creating tholins, complex organic molecules that give these objects their characteristic reddish-brown hue. The process is well understood. What is not well understood is why an interstellar comet, which should have formed in an entirely different stellar system under different conditions and traveled through the hostile emptiness of the galaxy, would bear such a striking resemblance to these distant relics of our own sun's family. The implication is clear and troubling. 3I Atlas has undergone extensive surface alteration. The question is where and over what timescale. Here's the problem. If the comet formed around another star, ejected by gravitational interactions, and then spent millions of years drifting through interstellar space, the cosmic ray exposure should have created a surface layer of modified ice and organics. That much is expected, but the data suggests something more. The crust is not a thin veneer. The modeling conducted by Maggiolo's team, drawing on decades of research into radiation chemistry and ice physics, indicates that galactic cosmic rays penetrate down to depths of 15 to 20 meters over the span of roughly 1 billion years. At those depths, crystalline ice, the orderly, structured form of frozen water, gets converted into amorphous ice, a disordered, glassy state. Secondary molecules form formaldehyde, methanol, carbon monoxide, carbon dioxide, and more complex organic chains. The surface of 3I Atlas is not simply weathered, it is armored. Now about the data. The James Webb Space Telescope's near-infrared spectrograph captured the coma during a 3-hour observation window on October 14, 2025, as the comet passed within 1.8 astronomical units of the Sun. That is roughly the distance of Mars at its farthest point from the Sun. Close enough for solar heating to begin sublimating the icy surface, releasing gas and dust into space. The spectrograph measured absorption features corresponding to water vapor, carbon dioxide, and carbon monoxide, along with fainter signatures consistent with methanol and formaldehyde. The SWIFT satellite, equipped with ultraviolet and optical instruments, provided complementary measurements of the dust production rate and the size distribution of particles in the coma. SPHEREx, NASA's newest all-sky infrared survey mission, added broad spectral context, mapping the comet's thermal emission and confirming the presence of organic materials across the entire visible surface. The combined dataset is unambiguous. The comet is expelling enormous quantities of carbon-rich volatiles. The water vapor, which typically dominates cometary outgassing, is present but overshadowed. Think about what that means. Water ice is the most abundant volatile in comets. It sublimates readily when heated by sunlight. It should be the primary component of the coma. Yet 3I Atlas is releasing water at a rate that is dwarfed by its carbon dioxide output. Either the surface is depleted of water ice, or something is preferentially releasing CO2 and CO while trapping water beneath. Maggiolo's team favors the latter explanation. Their models suggest that the organic-rich crust acts as a thermal insulator and a chemical barrier. When solar radiation strikes the surface, it heats the outer layers, causing the most volatile species, carbon monoxide and carbon dioxide, to sublimate first. These molecules, smaller and more mobile than water, can diffuse through the porous crust and escape into the coma. Water molecules, larger and more prone to hydrogen bonding, remain trapped within the ice matrix beneath the crust. The result is a coma dominated by carbon compounds, even though the bulk composition of the comet's interior might be water-rich. But that explanation raises another question. If the crust is thick enough and stable enough to trap water vapor, how thick is it really? The radiation models provide an answer, and it is one that has caused considerable debate. 15 to 20 meters. Picture a 6-story building. Now imagine that the entire surface of a comet, perhaps several kilometers in diameter, is covered by a shell of irradiated, organic-laden ice, as deep as that building is tall. The scale is staggering. This is not a light dusting of processed material. This is a fortress. Read between the lines of the published paper, and another detail emerges. The crust is not merely thick, it is stable. Most comets, when they approach the Sun, undergo dramatic outbursts. Pockets of volatile gas trapped beneath the surface suddenly break through, blasting away chunks of ice and dust in spectacular jets. The surface erodes, sometimes violently. New, pristine ice is exposed to sunlight, and the comet's activity surges. 3I Atlas has shown no such behavior. Its outgassing is steady, controlled, almost measured. The crust is not breaking apart. It is eroding slowly, layer by layer, in a manner that suggests the structure has remarkable cohesion. Some researchers have begun to use the word refractory, typically reserved for rocky materials that resist sublimation. The organic crust on 3I Atlas, it seems, behaves more like a solid shell than a fragile frost. Here's where things get strange. The chemistry of the crust, as inferred from the spectroscopic data, is more complex than simple irradiation models predict. Yes, cosmic rays can create tholins. Yes, they can generate formaldehyde and methanol from mixtures of water, carbon monoxide, and ammonia. But the spectral features detected by James Webb include absorption bands consistent with more elaborate structures, nitriles, polycyclic aromatic hydrocarbons, possibly even amino acid precursors. These are molecules that typically require not just radiation, but specific conditions of temperature, pressure, and chemical environment. They are the building blocks of prebiotic chemistry. They are the kinds of molecules that, on Earth, eventually gave rise to life. The official line from Maggiolo's team is carefully neutral. The organic inventory of 3I Atlas is rich and warrants further study, the paper states. The detection of complex carbon compounds is consistent with long-term exposure to galactic cosmic rays in a cold, radiation-dominated environment. True enough. But talk to the researchers off the record, and the tone shifts. One co-author, speaking on condition of anonymity during a conference call last week, admitted, "We are seeing molecules that, in laboratory settings, take very specific conditions to form. Cosmic rays alone might not be enough. There might have been liquid water at some point, or localized heating, or some other process we have not accounted for. Liquid water on an interstellar comet. The idea sounds absurd. Comets are frozen. They exist at temperatures barely above absolute zero, but the universe is not always so simple. Radioactive decay inside a comet can generate heat. Tidal forces during a close encounter with a planet or star can knead and flex the interior, producing frictional warmth. Impacts from other objects can deliver energy. If 3I Atlas is old, truly old, billions of years old, then it might have experienced such events. It might have had periods, however brief, when pockets of liquid water existed beneath its surface. In those pockets, chemistry could have happened. Molecules could have grown more complex. Structures could have formed. Scientists are not ready to say that 3I Atlas is carrying life, or even the remains of life. That claim would require far more evidence than spectroscopy can provide. But the possibility that the comet harbors prebiotic chemistry, molecules on the threshold of biology, is now openly discussed. And if that is true, then 3I Atlas is not just an interstellar traveler. It is a laboratory, a time capsule, a sample of the chemical conditions that existed in another star system billions of years ago. Think about what that means. The comet could have formed in the protoplanetary disk of a star that lived and died long before our sun ignited. It could have been ejected during the chaotic early phase of planetary system formation, when massive gas giants migrated inward and flung smaller bodies into interstellar space. It could have wandered the galaxy for eons, accumulating cosmic ray damage, growing its organic crust, preserving its primordial core. And now, by sheer chance, it has passed through our solar system, close enough for our instruments to examine it. But here's the unsettling part. The more astronomers study 3I Atlas, the more it seems purpose-built for preservation. The thick crust protects the interior from further radiation damage. The organic layer insulates against temperature fluctuations. The chemical composition suggests long-term stability. It is as if the comet is designed to survive, intact, across the vast distances and timescales of interstellar travel. Some researchers have begun to use the term Rosetta Stone, an object that contains information from a distant place and time, waiting to be decoded. Maggiolo himself has been more circumspect, but even he acknowledged the strangeness during a recent interview with the European Space Agency's Science Communication team. Nature has a way of creating structures that appear designed, but are simply the result of physical and chemical processes, he said. However, the degree of organization we observe in the surface layer of 3I Atlas is, I must admit, striking. It invites deeper investigation. That deeper investigation is already underway. The European Southern Observatory's Very Large Telescope in Chile is scheduled to observe 3I Atlas again in mid-November, using high-resolution spectrographs to search for additional molecular signatures. NASA's Hubble Space Telescope will map the comet's dust distribution in December, looking for clues about the structure and fragmentation of the crust. And next year, if funding is approved, the Atacama Large Millimeter Array will attempt to detect complex organic molecules directly, including amino acids and sugars. The challenge is time. 3I Atlas is already moving away from the Sun, back toward the outer solar system and eventually into interstellar space. Within 5 years, it will be too faint for current telescopes to study in detail. Within a decade, it will be gone, unreachable by any probe humanity could launch with existing technology. The window for investigation is closing. Every observation, every spectrum, every data point is precious. And yet, even with the data in hand, the fundamental mystery remains. Where did 3I Atlas come from? Not in the general sense, mass interstellar space, obviously, but specifically. Which star system? What kind of star? Was it similar to our Sun, or radically different? Was it a stable system with orderly planetary orbits, or a chaotic environment where collisions and ejections were common? The comet's chemical signature offers hints, but no definitive answers. The high carbon content suggests formation in a cold, carbon-rich disk, perhaps around a low-mass red dwarf star. The presence of complex organics suggests either a long residence time in the outer regions of that system or processes that enriched the primordial material before the comet even formed. Or both. Theoretical work on the origins of interstellar objects has accelerated in recent years, driven by the discoveries of 1I Oumuamua in 2017 and 2I Borisov in 2019. Oumuamua was an enigma. Its elongated shape, high velocity, and lack of visible outgassing led to wild speculation about its nature, including, notoriously, suggestions that it might be an artificial probe. Borisov, by contrast, looked like a perfectly ordinary comet, with a composition similar to solar system objects. 3I Atlas falls somewhere between. It resembles a comet in its structure and behavior, but its chemistry is exotic, more extreme than anything seen before. It is both familiar and alien. Some researchers have proposed that 3I Atlas originated in a young stellar system, one still surrounded by a massive debris disk rich in volatiles and organics. In such an environment, collisions and gravitational perturbations are frequent, and objects can be ejected into interstellar space at high velocities. The comet would then have spent millions or billions of years in the void, its surface slowly transformed by cosmic rays. This scenario fits the observations, but it is far from the only possibility. Another hypothesis suggests that 3I Atlas formed in the outer reaches of a mature planetary system, similar to our Kuiper belt, and was later ejected by a passing star. Such close encounters are rare but inevitable over the lifetime of a galaxy. A rogue star wandering through the outskirts of another system could gravitationally perturb the orbits of distant comets, sending some of them into interstellar space. If this happened billions of years ago, the comet would have had ample time to accumulate its organic crust while traveling through the galaxy. A third, more speculative idea has gained traction in certain circles, though it remains controversial. What if 3I Atlas did not form in a planetary system at all? What if it condensed in a molecular cloud, a vast region of cold gas and dust between the stars, before any star formed? Molecular clouds are rich in simple organic molecules. Formaldehyde, methanol, even amino acids have been detected in some clouds. If conditions were right, ices could clump together, accrete, and eventually form comet-like bodies within the cloud itself. These objects would then be dispersed when nearby stars ignited, their radiation blowing away the surrounding gas. The comets would be cast adrift, never having orbited a star, never having felt the warmth of a sun. They would be truly primordial, older than any planetary system. This last scenario is attractive because it explains the high organic content and the ancient processed appearance of 3I Atlas, but it is also deeply speculative. No one has observed comet formation in molecular clouds, and the physics of such a process is poorly understood. Most astronomers remain skeptical, yet the idea lingers, because it offers an answer to the question that keeps surfacing in private conversations and conference hallways. Why does 3I Atlas look so old? The radiation models are clear. To build a 15 to 20 meter crust of irradiated ice requires exposure to galactic cosmic rays for at least 1 billion years, possibly longer. That is an immense span of time. For comparison, the Earth is about 4.5 billion years old. The Sun has been burning for roughly the same duration. But individual comets in our solar system are not typically that old in the sense of having been isolated and exposed to space for 1 billion years. They spend most of their time in the Oort cloud or Kuiper belt, shielded to some extent by the Sun's heliosphere, which deflects a portion of the galactic cosmic radiation. Their surfaces evolve slowly, but not at the rate implied by the crust thickness on 3I Atlas. Interstellar space, by contrast, offers no such shielding. An object drifting between the stars is bombarded constantly by high-energy protons, helium nuclei, and heavier ions streaming from supernova remnants, active galactic nuclei, and other violent astrophysical sources. The radiation is relentless. Over hundreds of millions of years, it penetrates deep, altering ice structure, breaking chemical bonds, creating radicals and reactive species that recombine into new molecules. The surface darkens, reddens, hardens. The interior remains frozen, pristine, unchanged. 3I Atlas has lived this existence. It is a survivor, shaped by the galaxy itself. But survival on such timescales raises a philosophical question. What does it mean for an object to carry information across 1 billion years? The ice beneath the crust of 3I Atlas is, in a very real sense, a record. It contains the isotopic ratios of the gas and dust from which it formed. It may contain molecules that have not existed anywhere else in the galaxy for eons. It may even contain frozen and inert, organic structures that hint at the prebiotic chemistry of a long-vanished star system. All of this is locked away, protected by the very crust that makes the comet so mysterious. Some scientists have begun to wonder whether the preservation is accidental or functional. This is where the rhetoric becomes contentious. Maggiolo's paper carefully avoids any suggestion of intent or design. The crust, the paper argues, is a natural consequence of cosmic ray irradiation acting on a volatile rich surface over geological timescales. There is no need to invoke anything beyond known physics and chemistry. And yet, the way the system works, the insulation, the selective outgassing, the structural stability, has an almost engineered quality to it. It is efficient, it is robust, it is, in a word, protective. Read between the lines of the scientific discourse, and a deeper unease emerges. No one is suggesting that 3I Atlas is artificial. The idea is absurd, and no credible researcher would stake their reputation on such a claim. But the comet's properties do raise the question of whether interstellar objects in general might serve as vectors for chemical information. Panspermia, the hypothesis that life or its precursors can spread from world to world or even star to star, has a long and checkered history in science. It has been championed by serious researchers and ridiculed by skeptics in equal measure. The discovery of complex organics on interstellar comets does not prove panspermia, but it does show that the raw materials for life can survive interstellar travel. The crust on 3I Atlas is proof of concept. Given the right conditions, organic molecules can persist intact across the void. If that is true, then the galaxy is not a collection of isolated chemical laboratories. It is a network, a web of material exchange, where stars and planetary systems share their chemistry through the comets and asteroids they eject. Life on Earth might have started with ingredients delivered by comets from our own solar system. That much is already widely accepted. But if interstellar comets like 3I Atlas are common, and if they carry complex organics from distant star systems, then the chemistry of life might have origins that stretch far beyond the Sun's protoplanetary disk. The molecules in our cells might have histories that began in other stellar nurseries, under other suns, billions of years ago. This is speculation, but it is grounded in observation. The data from 3I Atlas are real. The organic molecules are real. The crust is real. The question is how to interpret these facts. Stop and consider that the comet is still out there, moving away from the sun at 16 kilometers per second, carrying its secrets with it. Every day, it travels another 1.4 million kilometers farther from Earth. The opportunity to study it will not last. And yet, even if humanity never sends a probe to intercept 3I Atlas, even if the comet vanishes back into the darkness from which it came, it has already changed the conversation. It has shown that interstellar objects are not uniform, not predictable, not easily categorized. Each one is a messenger from a different place and time, carrying information encoded in its chemistry and structure. The James Webb Space Telescope is scheduled for additional observations in early December, focusing on the infrared emission from the coma. The goal is to measure the temperature distribution and identify any thermal anomalies that might indicate localized outgassing or structural variations in the crust. If such features are found, they could provide clues about the internal structure of the comet and the mechanisms by which volatiles escape from beneath the organic layer. SWIFT, meanwhile, will continue monitoring the comet's dust production. Dust grains in the coma are thought to originate from the fragmentation of the crust as it sublimates. By analyzing the size distribution and composition of these grains, scientists hope to learn more about the physical properties of the organic material. Is it hard and brittle, like charcoal, or is it soft and porous, like soot? The answer will constrain models of crust formation and evolution. SPHEREx data still being processed will provide the broadest spectral coverage, spectral cover, spanning wavelengths from near ultraviolet to mid-infrared. This all-sky survey was not specifically designed to study comets, but its wide field of view and sensitivity to faint objects make it ideal for tracking the long-term behavior of 3I Atlas as it recedes. The mission's primary goal is to map the distribution of galaxies and measure the cosmic infrared background. But comets like 3I Atlas are serendipitous bonuses, offering snapshots of interstellar chemistry that complement the larger cosmological picture. Ground-based telescopes, too, are contributing. The Gemini Observatory in Hawaii and Chile has obtained high-resolution spectra of the comet's nucleus, attempting to separate the emission from the coma and isolate the faint reflected sunlight from the surface itself. Preliminary results suggest that the surface is extremely dark, with an albedo, the fraction of sunlight reflected, of less than 4%. For comparison, fresh asphalt has an albedo of about 7%. The crust on 3I Atlas is darker than asphalt. It is one of the darkest surfaces ever observed on a solar system object, rivaling the nuclei of dead comets and certain carbonaceous asteroids. This is consistent with a thick layer of organic tholins, which absorb nearly all visible light. The darkness has implications. A dark surface absorbs more solar energy, which should drive stronger outgassing. Yet 3I Atlas is not particularly active compared to other comets at similar distances from the Sun. The contradiction suggests that the crust is not only dark, but also thermally insulating. Heat from the Sun is absorbed by the surface, but it does not efficiently penetrate to the underlying ice. The organic material acts as a blanket, preventing the interior from warming up. This is consistent with the thick crust model, but it also means that the comet is less responsive to solar heating than a typical comet would be. It is insulated, protected, preserved. All of this brings the discussion back to the central mystery. What is 3I Atlas hiding? The word hiding is loaded, of course, implying agency or intent. But strip away the anthropomorphism, and the question remains valid. What lies beneath the crust? The radiation model suggests that the interior is composed of pristine, unprocessed ice, potentially containing isotopic ratios and molecular abundances that reflect the conditions in the comet's birthplace. That interior is, effectively, a frozen sample of another star system's protoplanetary disk. If scientists could access it, drill through the crust, extract a core sample, analyze the ice in a laboratory, they would gain direct insight into the chemistry of planet formation elsewhere in the galaxy. But accessing the interior is, for now, impossible. No space mission has been planned or funded to rendezvous with 3I Atlas. Even if such a mission were approved today, it would take years to design, build, and launch the spacecraft, and by that time the comet would be too far away for a feasible intercept. The trajectory and velocity of 3I Atlas are such that catching up to it would require an enormous amount of propulsion, far more than current chemical rockets can provide. Nuclear propulsion, solar sails, gravitational assists. These are options in principle, but not in practice, not with the lead times involved. This has led to frustration within the planetary science community. Oumuamua came and went before anyone realized what it was. By the time its interstellar origin was confirmed, it was already receding beyond the reach of any conceivable mission. 2I Borisov was discovered earlier in its passage, and there was brief discussion of a fast flyby mission, but the technical and financial hurdles proved insurmountable. 3I Atlas now is the third confirmed interstellar object, and once again humanity is relegated to the role of passive observer. Telescopes can gather light, spectrographs can analyze chemistry, but the comet itself remains untouchable. Some researchers have proposed a different strategy. Be ready for the next one. Statistical estimates, based on the discovery rate of interstellar objects and the limitations of current survey telescopes, suggest that dozens or even hundreds of such objects pass through the inner solar system every year. Most are too small or too faint to detect. But with improved survey capabilities, wider fields of view, faster cadences, more sensitive detectors, it should be possible to spot interstellar visitors earlier when they are still inbound, and a mission might be feasible. NASA and ESA have both commissioned studies on rapid response spacecraft that could be built and stored in a state of readiness, waiting for a suitable target. The concept is similar to emergency response systems on Earth. Keep the hardware on standby, and when an alert comes in, launch within weeks or months rather than years. Such a spacecraft would need to be modular, adaptable, and capable of high delta-V maneuvers. It would carry a minimal suite of instruments, cameras, spectrographs, perhaps a dust analyzer or impactor probe, but it would get to the target while the window of opportunity is still open. Whether such a mission will ever be funded remains uncertain. The political and financial realities of space exploration are complex, and interstellar objects, however scientifically compelling, must compete for resources with missions to Mars, Europa, Titan, and the outer planets. But the case for prioritizing interstellar visitors is growing stronger with each new discovery. 3I Atlas is the latest piece of evidence that these objects are not mere curiosities. They are archives, time capsules, Rosetta Stones. They offer information that cannot be obtained any other way. Meanwhile, theorists are working to understand the population of interstellar objects in the galaxy. How many are out there? How are they distributed? What is the typical ejection velocity from a planetary system? How long do they survive before colliding with a star or being torn apart by tidal forces? These are questions that blend astrophysics, planetary science, and galactic dynamics. The answers will inform not only the search for future interstellar visitors, but also the broader understanding of how planetary systems evolve and interact. One intriguing line of research focuses on the possibility that interstellar objects can be gravitationally captured by stars. If an object passes close enough to a star at just the right velocity and angle, it can lose enough energy to be trapped in an orbit, effectively becoming part of that star's planetary system. Numerical simulations suggest that this happens rarely, but over billions of years, even rare events add up. Some objects in our own Kuiper belt or Oort cloud might be captured interstellar comets, indistinguishable from native objects except for subtle differences in composition or orbital characteristics. The idea is tantalizing. Hidden among the trillions of comets surrounding the Sun, there might be dozens or hundreds of interstellar interlopers, ancient wanderers that arrived from other stars long ago and have been orbiting quietly ever since. If that is true, then missions to the outer solar system, missions like New Horizons, which flew past Pluto and the Kuiper Belt object Arakoth, might have already encountered interstellar material without realizing it. Future missions, equipped with more sophisticated compositional instruments, could test this hypothesis by looking for anomalous chemistry in trans-Neptunian objects. A comet with carbon dioxide and carbon monoxide ratios like 3I Atlas, for instance, would be an immediate candidate for interstellar origin. But even without captured objects, the study of interstellar comets like 3I Atlas is reshaping the field of astrobiology. The traditional focus of astrobiology has been on planets, Earth-like worlds and habitable zones, Mars with its ancient riverbeds, Europa and Enceladus with their subsurface oceans. Comets were always part of the conversation, but as delivery vehicles, not as environments in their own right. 3I Atlas is changing that perspective. If the comet harbors complex organics, if it potentially had liquid water at some point in its history, if its chemistry is rich enough to support prebiotic reactions, then it is not merely a carrier of ingredients. It is a participant in the story of life's origins. This has led some astrobiologists to propose that interstellar comets should be considered potential habitats, not for active life, but for the processes that lead to life. The interior of a large comet, insulated by a thick crust and warmed by radioactive decay, might maintain liquid water for millions of years. In that environment, organic molecules could dissolve, react, and grow more complex. Lipid membranes could form, encapsulating pockets of solution. Polymers could assemble. None of this requires life, in the sense of metabolism and reproduction, but it moves chemistry closer to the threshold. And if such processes occurred in 3I Atlas or in other interstellar comets, then the galaxy might be seeded not just with organic molecules, but with protocellular structures, the immediate precursors to life. This is, admittedly, speculative. No one has detected lipid vesicles or polymers in the coma of 3I Atlas. The data show organics, yes, but simple organics, tholins, nitriles, polycyclic aromatics. Complex, perhaps, but not biological. Yet the fact that the conversation has shifted this far is itself remarkable. 5 years ago, interstellar objects were barely on the radar of astrobiologists. Now they are central to the discussion. Think about what that means for the search for life beyond Earth. If complex chemistry can arise in comets, and if comets can travel between stars, then the processes that lead to life might be distributed across the galaxy. A molecule synthesized in one star system could end up in another, incorporated into a planet or moon, influencing the chemistry there. The biosphere of Earth might be, in part, a product of interstellar chemistry. And if that is true here, it is likely true elsewhere. Life, or at least the chemistry that enables life, might be a collective phenomenon, emerging not from the isolated conditions of individual worlds, but from the shared chemical heritage of the galaxy. This is a profound shift in perspective. It transforms the origin of life from a local problem, how did chemistry on early Earth lead to biology, into a galactic problem. How does chemistry, distributed across countless star systems and carried by interstellar comets, lead to biology wherever conditions are favorable? The answer might be that life is not an unlikely accident, but an inevitable outcome of a galaxy that is chemically connected. But these are ideas for the future, Right now, the focus is on 3I Atlas and the data it is providing. Every observation adds a piece to the puzzle. The carbon dioxide ratio tells us about the comet's thermal history. The carbon monoxide abundance hints at formation conditions. The organic signatures reveal the complexity of the chemistry. The crust thickness constrains the age and exposure history. Taken together, these pieces form a picture, still incomplete but growing clearer. And yet, for all the data, the fundamental question remains unanswered. What exactly is 3I Atlas? Is it a fragment of a failed planet, ejected during the chaotic assembly of a solar system? Is it a pristine remnant of a protoplanetary disk, preserved in the cold of interstellar space? Is it a body that formed in a molecular cloud, older than any star? Or is it something else entirely? Something that defies easy categorization. The comet does not offer answers. It simply exists, moving through space, outgassing slowly, shedding atoms and molecules into the void. But in that very silence, there is a kind of message. 3I Atlas is a reminder that the universe is full of objects and phenomena that humanity is only beginning to understand. Every discovery, every anomaly, every unexpected data point is an invitation to look deeper, to question assumptions, to expand the framework of knowledge. Here's where things get strange. As astronomers have pored over the data in recent days, a small but growing number have begun to ask whether the crust on 3I Atlas is unusual, even by the standards of interstellar objects. The sample size is admittedly small. Only 3 confirmed interstellar visitors, and only 2 of them comets. But 2I Borisov, the other interstellar comet, showed no evidence of an organic-rich crust. Its outgassing was dominated by water vapor, its color was relatively neutral, and its composition was broadly similar to solar system comets. It was, in short, unremarkable. 3I Atlas, by contrast, is anything but. This raises the possibility that there are different classes of interstellar comets, shaped by different formation environments or evolutionary histories. Borisov might represent comets ejected from young, dynamically active planetary systems where volatiles are abundant and organic processing is limited. 3I Atlas, on the other hand, might represent a population of older, more evolved objects, possibly ejected from mature systems or formed in interstellar space itself. If that is the case, then the diversity of interstellar objects might be far greater than anyone anticipated. Some researchers have even speculated that 3I Atlas might not be a comet in the traditional sense. Its behavior, steady, controlled outgassing, minimal fragmentation, extreme surface darkness, is more reminiscent of certain types of asteroids, particularly the carbonaceous chondrites, which are rich in organic material and water, but structurally more robust than icy comets. Could 3I Atlas be a hybrid object, part ice and part rock, with a structure that blurs the line between comet and asteroid? The data do not rule it out. The low albedo and organic-rich surface are consistent with carbonaceous material, and the high carbon dioxide and carbon monoxide could be released from mineral-bound volatiles rather than pure ice. If 3I Atlas is indeed a hybrid, it would fit into a broader category of objects known as active asteroids. Bodies that have asteroid-like orbits and structures, but occasionally release gas and dust like comets. Several such objects have been identified in the asteroid belt, and they are thought to be the result of either subsurface ice being heated by the sun or volatile-rich minerals breaking down. An interstellar active asteroid would be a first, but not implausible. The debate over the nature of 3I Atlas is ongoing. Maggiolo's team maintains that the comet designation is appropriate, given the observed outgassing and coma, but they acknowledge that the object is unusual and that further observations might require a refinement of the classification. For now, 3I Atlas remains officially categorized as a comet, but with an asterisk, figuratively speaking, acknowledging its atypical properties. What comes next depends on the comet's trajectory and the instruments available to observe it. The window for high-quality spectroscopy will close by the end of this year, as 3I Atlas moves beyond the reach of the largest telescopes. After that, only the brightest and most sensitive instruments will be able to detect it, and the data will be limited to broad photometric measurements, essentially tracking the comet's brightness and color as it fades into the distance. By late 2026, it will be too faint for even those measurements, and 3I Atlas will vanish from human ken, another silent traveler in the vastness of space. But the scientific impact will endure. The data gathered over the past few months will be analyzed and reanalyzed for years, mined for insights that might not be apparent at first glance. Theoretical models will be refined, incorporating the new constraints provided by 3I Atlas. Surveys will be redesigned to detect more interstellar objects earlier, increasing the chances of a timely mission. And astrobiologists will continue to ponder the implications of complex organics surviving interstellar travel and what that means for the distribution of life's building blocks across the galaxy. In the meantime, astronomers will watch the skies, waiting for the next interstellar visitor, the 4th, the 5th, the 10th. Each one will bring new data, new surprises, new mysteries. And each one will be a reminder that the solar system is not an island, isolated and self-contained. It is a waypoint, a crossroads, a place where the galaxy's wanderers pass through, leaving traces of their distant origins. 3I Atlas is one such wanderer. It arrived unannounced, swept through the inner solar system, and is now departing, its secrets only partially revealed. The comet has shown astronomers that interstellar objects are not all alike, that the chemistry of other star systems can be profoundly different from our own, and that the processes shaping these objects over cosmic timescales are more complex than simple models suggest. It has also shown that the universe is full of surprises, that every new observation has the potential to overturn expectations, and that the pursuit of knowledge is an endless journey into the unknown. And so the question lingers, unanswered and perhaps unanswerable, with current data. What is 3I Atlas protecting beneath its 20-meter crust? What frozen record of another world, another star, another era of the galaxy's history is locked within? Is it merely ice and organics, the natural detritus of planet formation? Or is it something more? A chemical legacy, a prebiotic archive, a message written in molecules that traveled across light years and eons to reach this place, this moment, this fleeting encounter with humanity? Read between the lines of the scientific papers, listen to the careful phrasing of the researchers, and the sense of wonder is unmistakable. 3I Atlas is not just a comet. It is a question posed by the universe itself, and the answer, if it exists, remains hidden beneath layers of ancient ice, shielded by a crust that has withstood 1 billion years of cosmic radiation, waiting for a species capable of asking the right questions and possessing the technology to uncover the truth. But time is running out. The comet is moving away. The instruments are straining to gather the last photons of reflected sunlight. The window is closing, and when it shuts, 3I Atlas will carry its secrets back into the void, leaving behind only data, speculation, and the tantalizing possibility that somewhere in the frozen heart of an interstellar wanderer, there lies an answer to one of the deepest questions humanity has ever asked. Are we alone? The comet does not answer. It simply moves, silent and inscrutable, through the darkness between the stars. But silence, in this case, may be the most eloquent response of all. Consider what has happened in the 3 weeks since Maggiolo's team released their preliminary findings. The paper has been downloaded more than 40,000 times. It has been cited in 6 follow-up studies, 3 of which are still in preprint and have not yet undergone peer review. The data have been reanalyzed by independent groups in Japan, Australia, and the United States, each applying different modeling techniques, different assumptions about radiation chemistry and ice physics. And in every case, the conclusions converge on the same unsettling point. The crust is real, the chemistry is extreme, and the timescales involved are staggering. No one is saying the comet is artificial. That word does not appear in any published paper, and it will not, because the moment a scientist uses it in a formal context, their credibility evaporates. But strip away the taboo, ignore the career-ending implications, and ask the question plainly. Does 3I Atlas behave like an object shaped purely by chance and physics? Or does it behave like an object optimized for a specific function? The crust protects, the chemistry preserves, the structure endures. These are facts. The interpretation of those facts is where the controversy begins. Read between the lines of the latest ESO observing proposal, submitted just last week by a consortium of European researchers, and the language is telling. The proposal requests 60 hours of telescope time on the Very Large Telescope, specifically to search for what they term chemical gradients in the coma. Chemical gradients mean layers. Layers mean structure. Structure means organization. The proposal does not say this explicitly, but the implication is clear. The researchers want to know if the outgassing pattern of 3I Atlas is uniform, or if certain molecules are being released preferentially from specific regions of the surface. If the latter, it would suggest that the crust is not homogeneous, that it has zones or domains with different compositions, different thicknesses, different properties. And if that is true, then the question becomes why? What process could create such organization? Natural processes, certainly. Differential heating as the comet rotates could create temperature gradients, which in turn could affect sublimation rates. Impact craters could expose fresh ice in some areas, while leaving the crust intact in others. Variations in the original composition of the nucleus, dating back to its formation, could manifest as differences in the crust properties after billions of years of irradiation. All of these explanations are plausible, and all of them are being explored in the current modeling efforts. But there is another possibility, one that hovers at the edge of respectability, mentioned only in private or in the speculative sections of conference presentations. What if the organization is not incidental but functional? What if the crust has adapted, in some sense, to the environment it has traversed? Not adapted in the biological sense. No one is suggesting the comet is alive, but adapted in the way that a structure subjected to relentless environmental pressure will, over time, reach a configuration that maximizes stability. The technical term is self-organization, a phenomenon observed in systems ranging from sand dunes to snowflakes to the large-scale structure of the universe itself. Given enough time and the right conditions, simple physical laws can produce patterns that appear designed. 3I Atlas has had time, 1 billion years, possibly more, and the conditions, constant cosmic ray bombardment, extreme cold, the slow chemistry of ice and organics, have been stable for almost all of that duration. Could the crust have self-organized into a configuration that maximizes the comet's survival? Could the very properties that make 3I Atlas so unusual, the thickness, the darkness, the insulating behavior, be the result of a billion-year annealing process where less stable configurations eroded away and only the most robust structure remained? This is not panspermia. This is not directed panspermia, the idea that life or its precursors were deliberately sent across space by an intelligent civilization. This is something more subtle and in some ways more disturbing. The possibility that the universe itself, through nothing more than time and physics, can create objects that look purposeful, that the line between design and emergence, between intent and inevitability, is not as clear as human intuition suggests. Stop and consider the implications. If 3I Atlas represents a stable endpoint of interstellar comet evolution, then there should be others like it, many others. And if such objects are common, then the organic crust they carry is common, and the complex molecules within that crust are common, and the potential for those molecules to seed prebiotic chemistry on planets is common. The galaxy is not just filled with rocks and ice, it is filled with chemistry, ancient and complex, distributed across every cubic light year, waiting for the right conditions to become something more. Here's where it gets strange again. In the last 72 hours, 3 separate research teams have independently proposed that 3I Atlas should be observed in the radio spectrum. Not the infrared, not the optical, but radio wavelengths. Specifically in the range where complex organic molecules emit characteristic signals. The rationale is straightforward. If the comet's crust contains long-chain hydrocarbons, nitriles, or even amino acids, those molecules might be detectable directly, without having to infer their presence from secondary indicators like color or thermal emission. Radio observations would provide unambiguous identification, molecule by molecule, building a complete inventory of the crust's composition. The challenge is sensitivity. The comet is faint, and radio emission from organic molecules is weak. Detecting it would require one of the world's most powerful radio telescopes, operated at its limits, staring at a single point in the sky for hours or days. The Atacama Large Millimeter Array, ALMA, is the obvious choice. It has the sensitivity, the resolution, and the frequency coverage. But ALMA is oversubscribed, with far more requests for observing time than can be accommodated. Proposals are ranked by scientific merit, and while 3I Atlas is undeniably interesting, it must compete with studies of distant galaxies, star-forming regions, and exoplanet atmospheres. The allocation committee will meet in mid-November. The decision will come down to priorities, politics, and luck. If the observations are approved and conducted, and if they succeed in detecting complex organics, the impact will be immediate. Amino acids on an interstellar comet would be front-page news, not just in scientific journals, but in mainstream media. It would reignite the panspermia debate, not as idle speculation, but as a testable hypothesis grounded in observational data. And it would force astrobiologists to confront a question they have largely avoided. If the building blocks of life can survive interstellar travel, and if interstellar comets are common, then why should life be rare? The traditional answer has been that building blocks are not enough. Life requires not just molecules, but environments where those molecules can interact, concentrate, and evolve. A comet's interior might provide such an environment if it ever had liquid water, but the conditions would be transient and limited. A planet, by contrast, offers stability, energy, and the vast timescales necessary for biology to emerge. This is the consensus view, and it is probably correct. But 3I Atlas is chipping away at the edges of that consensus. The comet has shown that complexity can persist for billions of years, that organic molecules can be preserved in structures that resist degradation, that chemistry does not stop just because an object is isolated in the void. If one comet can do this, so can others. And if enough comets carrying enough organic material impact enough planets over enough time, then the chemistry of life becomes not a local accident, but a distributed phenomenon, occurring wherever conditions allow. Think about what that means for Earth. The planet formed 4.5 billion years ago, and life appeared relatively quickly afterward, within a few 100 million years. That rapid emergence has always been puzzling. The early Earth was hostile, volcanic, bombarded by asteroids, with an atmosphere of nitrogen, carbon dioxide, and water vapor, but little oxygen. Yet somehow, in that environment, organic molecules assembled into structures capable of metabolism, reproduction, and evolution. The question has always been, where did the organics come from? Comets have long been part of the answer. The late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets, likely delivered vast quantities of water and organic material to Earth. But those comets came from the Oort cloud and Kuiper belt, formed in the Sun's protoplanetary disk, carrying chemistry that reflected local conditions. What if some of those comets were interstellar? What if objects like 3I Atlas, or their ancient equivalents, also struck the early Earth, delivering not just water and simple organics, but complex molecules pre-processed by billions of years in space? The chemistry of life on Earth might have a pedigree stretching back not 4.5 billion years but far longer, to star systems that existed and died before the Sun was born. This is speculation, but it is grounded in fact. 3I Atlas exists. Its crust exists. Its chemistry exists. The only question is how many others like it have passed through the solar system, undetected, over the past 4 billion years. Statistical estimates suggest thousands, perhaps tens of thousands. If even a small fraction of them impacted Earth, they could have contributed significantly to the planet's organic inventory. But here's the problem, and it is one that Maggiolo's team has discussed at length in their internal communications, though not yet in public. If interstellar comets contributed to the origin of life on Earth, then they likely contributed to the origin of life elsewhere. The chemistry is not unique. The process is not unique. The timescales and conditions required are met in countless star systems across the galaxy. Life, or at least the chemistry that enables life, should be common. Not inevitable, but common. And if life is common, then intelligent life, given enough time and the right evolutionary pressures, might also be common. And yet, the galaxy is silent. No signals, no megastructures, no evidence of civilizations beyond Earth. The Fermi paradox, in other words, remains unresolved. 3I Atlas does not answer it. If anything, the comet makes the paradox sharper. The more evidence accumulates that the building blocks of life are abundant, the more puzzling the silence becomes. Some researchers have begun to wonder if the silence itself is the message. Not that life is rare, but that something prevents it from spreading, from becoming visible on galactic scales. Extinction events, resource limitations, self-destruction. These are the usual explanations, but there is another possibility, darker and more speculative. What if intelligence arises frequently, but chooses not to expand, not to signal, not to make itself known? What if the universe is full of civilizations that have looked outward, seen the dangers or futility of contact, and withdrawn into silence? This is the kind of thought that emerges late at night, in the hours after a long day of data analysis, when the mind is tired and the usual filters are down. It is not science, not yet, but it is the kind of thinking that science sometimes inspires. 3I Atlas, in its silence, invites such thoughts. The comet has traveled so far, endured so much, carried so much information, and yet it offers no answers, only more questions. The researchers studying the comet are acutely aware of this. They know that their papers, their models, their observations will be scrutinized not just for scientific accuracy, but for implications. Every word is chosen carefully. Every conclusion is hedged with caveats. The data are real, but the interpretations are provisional, subject to revision as more information becomes available. This is the nature of science, but it is also a form of self-protection. To claim too much, to speculate too boldly, is to risk ridicule, or worse. And so the discourse remains measured, careful, constrained by the norms of academic publishing and professional reputation. But outside those constraints, in blog posts and social media and popular science articles, the speculation runs wild. 3I Atlas has been called a doomsday comet, a galactic messenger, a biological time bomb, and worse. None of these labels are accurate, and most are sensationalist nonsense. But they reflect a deeper truth. The comet has captured the public imagination in a way that few astronomical discoveries do. It is not just a rock in space. It is a story, a mystery, a puzzle that invites interpretation. And stories, unlike data, are not constrained by error bars and confidence intervals.